It's our pleasure to start off the Probability Analysis webinar 2020. Our very first speaker is Felipe Gonçalves, and he's going to speak about sign uncertainty. And let me just remind everybody that this meeting is being recorded, so if you do not wish to be recorded, please turn off your cameras. Felipe, go ahead.
Well, thanks. Thanks for the invitation to speak here. It's a pleasure. So let me just jump and start. So basically, this talk is going to be about this kind of a new sign uncertainty principles. It started in 2010, this whole business with a paper of Bourgain. And it turns out that these uncertainty principles are connected with sphere packing, the sphere packing problem. So that's what I'm going to try to explain in this talk, how these, first of all, explaining these uncertainty principles, then how they are connected with sphere packing. And the promise of the talk is to show how, why these problems are so interesting and have some mysteries behind it. At least for me, it's some kind of a Pandora box. When you try to investigate something, it turns out it's connected with something else, and etc. Okay. So let's start. And the picture here is more or less how we'll see these uncertainty principles, like a tug of war between a function wanting to be positive at some places and negative at other places. Okay. So let's start with the simple definition. We'd say, so suppose you have a function on RD and it's real valued, and suppose you want to know if it, so we define a function to be eventually non-negative if at some point on, so outside of a large ball, the function is greater or equal than 0. Okay. And then we define R of f, the radii of the smallest ball, such that outside that ball, the function is greater or equal than 0. Okay, so the R of f would be the last sign change of f. So the typical picture is something like this. So this will be like, say, in one dimension. This is an even function. It starts doing something here. And then at some point, let's say around 3, it becomes greater or equal than 0 and it stays like this. So that would be a typical picture you will see here. So then you can define the following class. So it would be the A plus class. So f and f hat being the Fourier transform, both L1 and even, and real valued. So you have just two functions, both f and f hat, L1, etc. and real valued. Okay, they have to be even so that both are real valued. And then you will require that the mass of the functions are both less or equal than 0. So f hat at 0 and f at 0 both less or equal than 0. And then we require that both f and f hat are eventually non-negative. So both functions outside of a large ball, they're greater or equal than 0. And then one quantity of interest here is when you multiply R of f with R of f hat. Because, well, this is scaling invariant. So if you multiply, let's say, the variable x in the function f by lambda, then the Fourier transform gets divided by lambda. So if you multiply these two things here, it becomes, it stays invariant. And we like to take the square root here just to normalize. So you want to minimize this quantity. So you want to figure out if you can have both f and its Fourier transform greater or equal than 0 outside arbitrarily small neighborhood of the origin. If that is possible or not. And if it's not possible, what lower bound can produce? So this sort of question was investigated in 2010 by Bourgain, Clozo, and Kahan in connection with bounds for discriminant of number fields, which I'm not going to talk about. But these were the auxiliary functions they were studying, and it turns out they made almost like 70% of the paper about the auxiliary functions, and then 30% about these applications related to discriminant of algebraic number fields. But what they end up proving, and it's indeed you have an uncertainty principle here, so you can't make R of F and R of F hat arbitrarily small. So the lower bound here is exactly the statement of the certainty principle that they proved. They actually managed to show that the lower bound grows as square root of D, and then by playing a little bit with some polynomials times Gaussians, you can come up with some pretty decent functions that give you the same asymptotic behavior for an upper bound, for instance, and then they derive these bounds here. Okay, so basically, and then what it turns out, and that's like the big surprise, is that in 2019, we were able to solve this problem exactly and to show that in 12 dimensions, the answer is the square root of 2, which is a kind of a surprising thing if you don't know where it comes from, and why square root of 2 and why dimension 12 and not any other dimension. So, and so that's my goal of this talk, to explain why this has to be the case and where this comes from. Okay, any questions so far?
Is this number known for other dimensions?
Yeah, you will see in a moment. Yeah, that's part of the surprise. Okay, so any other question? Great, so let's move on. So before we try to answer Patra's question, let me just explain a little bit about the proof. So in here, in the definition of the class, we have this plus sign. And let me explain why we have this plus sign here. So the proof has a reduction, and this Bourgain realized already, and Bourgain and the other authors. So first of all, since we are using balls in RD, of course, we can make F radius. So if you, with the thought of you trying to find the best function for this uncertainty principle, you can think of trying to make some reductions. And the first, the obvious one is to make FM radial. And again, since we're using RF times RF hat, and that's scaling variant, you can just play with the scaling factor and force F and F hat to have the same last sign change. Because when you squeeze F, you dilate F hat. So then at some point, the R of F has to be equal. And once you have that, then you can just add the functions, for instance. And that would still be in the class, and that would do a job just as good as the function before. And then by subtracting a Gaussian, you're still in the class, but then you force the linear condition, which was the mass. So if you recall, let me go back in the definition, we have here the mass of both functions being less or equal than 0. So you can force that quantity, that linear condition to be attained just by subtracting a Gaussian. So then you end up showing that the following reduction. So A plus D is actually the infimum of just R of F, and that's why we use the square root. So in the end, it's just R of F. So in the normalization here, that's why we use the square root. So you're just minimizing the last sign change of a radial function, which self-dual, it has 0 mass, and it's eventually non-negative. So that's why we call A plus, because this plus here is related with the fact that the function is a +1 eigenvalue of the Fourier transform rather than a -1 or a plus or minus I, for instance. So that's where the +1 comes from. And so that's the typical picture. You see, so in dimension 2, I just plotted the radial function here. And if you know a little bit about Laguerre polynomials and why they are, how they are related with the Fourier transform, how they operate, you can pretty much figure out a way of constructing functions in this class here, in this red box here. And it's pretty much you use the correct Laguerre polynomials, and then you try to force the linear conditions that you have to satisfy. And then in the end, you can pretty much, in the end, you figure out it's more or less easy to come up with examples of functions in this class. And this is just one example. It's a polynomial degree 4 times a Gaussian, and it changes more or less around the square root of 2 over pi. No, exactly, sorry, square root of 2 over pi, that's the last sign change. It does not do a good job in dimension 2. We can make functions that do a much better job, but this is just an example to say that the class is non-empty. But you get several examples there. Okay. So naturally, you can think about, well, since we have the +1 problem, maybe we have a -1 problem. So a +1 uncertainty principle, then maybe you have a -1, and that's the case, actually. So basically, if you just go back to the definition I did here for the plus class and just put minus in the correct places, you end up with a -1 uncertainty principle, which is very different. They're not so different, but they are different, but they're kind of a cousin problems. So the -1 is pretty much the same. So you have f and f hat, both even and real valued. You have both f and now minus f hat, eventually no negative. So here the model is f hat equals minus f. So if f is eventually no negative, then minus f hat should be eventually no negative. And you again require that the mass of f, so f hat of 0 is less or equal than 0, and the mass of f hat, so f of 0 is greater or equal than 0, so minus f of 0 less or equal to 0. So that would be the kind of cousin or brother, or I don't know the term you like to put, problem associated. So you can then make the same thing, try to minimize R of f and R of f hat. So you have to put a minus here because I define R of f as the function be eventually positive. So I have to put a minus there, just for a technicality. So you can try to minimize the same quantities. And then in 2018, we showed basically the same. We were able to prove that indeed we have an uncertainty principle. We still get the same exact lower bound, same as Bourgain derived, but the upper bound is slightly better. We have, so the previous upper bound was just with 1 divided by square root of 2 pi, but you can subtract this little factor here. And then again, that comes from the connection with sphere packing and bounds for sphere packing that I will explain in a moment. And you can...
I'm sorry, I just wanted, there's a question in the chat.
Oh.
Is there any assumption made about the distribution of this function as the theorem inequality, or this inequality can be used in any scenario that it is invariant and universal? I refer to the expression in the BCK 2010 theorem that determines or bounds the sign inequality.
So, yeah, so there is no extra assumption in the function, if I understood correctly the question.
Yeah, if there's any assumption made about the distribution.
Where I can see the chat.
It's really
Yes.
hard to see when you figured you saw it?
Yeah, yes, yes.
Okay.
No, this basically is just any function. For everything to work nicely, you have to require the f and f hat are both in L1. So if you're thinking about making f being a measure somehow or something like that, maybe it's not going to work. I don't know, or maybe it works. I don't know.
Felipe,
Yes.
I'm not sure whether I understand the question correctly, but maybe the upper bound, it's not for every function, right?
There's
It's
upper bound?
specific function.
No. Yes. So So my notation here is this: we have this this A here, this like a fancy A for the class, and this other A for the infimum of this quantity over the class. Okay. So for every function in the class, you have this lower bound. So this is the infimum of the quantity, which means that the upper bound basically means that there is a function which does this job. Because this is the infimum of the class.
Do you have characterizations for such functions?
Yeah, so this is just a bound. So there is a function that does a pretty good job, let's say, in the sense that it captures the asymptotic behavior because I'm dividing by square root of t here. That's what I'm saying by this upper bound here. Maybe I should state that, maybe I should write it in another way. Maybe I should write, there is a function that does this job. But this is exactly the same. Maybe I could write this better, but that's what this means. It means that since this is the infimum here, it means that there is a function f such that this thing is, that does a job like this. Okay, that's what I mean. I don't know if that satisfies the question. Is that okay?
Yep, thank you.
Yeah. So, so basically what you have to think about is that the quantities A plus or minus here, they behave like a constant times square root of d. You're not sure what the constant is. To get a lower bound for the constant, you have to like prove the lower bound for every function in the class. So prove the upper bound for this constant, you just have to exhibit one. That's what I was saying. So in 2018, we discovered that there is this cousin uncertainty principle, and you can sort of make the same reductions as before, like make it radial and then play with the scaling. So make R of f equals R of f hat. And then you can sort of add the Gaussian. It's not exactly adding a Gaussian, a bit more complicated. You have to add 4 Gaussians to make it work, but you can force f hat, f at 0 be 0, and etc. So you can make the sort of same reductions, and then you realize that this is exactly the same problem as before, just with, instead of self-dual functions, you have anti-dual functions, f hat equals minus f, okay? So nowadays we call these inequalities. So typically an uncertainty principle is a name of an inequality. So to be rigorous here, so we call these inequalities here, the A plus D greater or equal than some constant times root D, the plus or minus 1 uncertainty principles, or plus or minus 1 sign uncertainty principles. Okay, any other question?
Hello, I'm Min. I'm a probabilist. I'm just curious, why is this inequality called uncertainty principle? Just something intuitive.
Oh, sure. So usually, at least for me, usually when you have a certain class of functions and you have a quantity associated to each function of that class, and when you somehow you multiply these two quantities for f and f hat, and that has a lower bound, meaning that you have an uncertainty principle in that way.
Mm-hmm. Thanks.
Yeah, you're welcome. So, so that's and another way of answering this question. We're just also following what Bourgain did. What Bourgain called this an uncertainty principle. We also think it's an uncertainty principle, and it has all the ingredients. At least for us, it has all the ingredients of being an uncertainty principle. Okay, so let's move on. Great, and just before we start to talk about the connections with sphere packing, let me just finalize this part about the uncertainty principle, about what we know about these functions, okay? What we do know so far is that We can prove existence of optimal functions. So if there is a function in the class where we can make all the assumptions, all the reductions I presented before. We can assume its ratio. We can assume that f hat equals plus or minus f, and then f of 0 is 0. And that then R of f attains the infimum among the class, okay? And we can say something more about it. We can say that if you consider f as a radial function, that as a function of the radii, it has several double roots after the last sign change. Oh, sorry, after the last sign change. So basically, what you have is a function that after the last sign change, it goes back and touches the x-axis several times, okay? That's the only thing we can prove so far. We don't know how these zeros are distributed. You will see in a moment that how these zeros are distributed into 12 dimensions that we know. And for the -1 problem, we know how to solve that in 8 and 24 dimensions. So you see that in a moment. And we know how the zeros are distributed there as well. But in general, we have no idea how they are distributed. This is more or less what all we know in general about these functions.
Felipe,
Yes.
do you know if any of these conditions is also necessary?
What conditions?
For example, the infinitely many double roots after the sign change.
Yes, so we know that if f is optimal, then it must have infinitely many double roots. That's what I mean.
Okay, okay.
Yes. Yes, because for any function in the class, you can more or less remove all double roots, just make the function strictly greater than 0 after the last sign change. But then you have to make the last sign change a bit worse. You have to increase it by a little bit. So you can make the function a little bit worse by removing all the roots. But then it's not going to be optimal. If it is optimal, if it's R of f is as small as it can be, then you must have a bunch of double roots later after. Okay, that's what I mean.
Thanks.
We can even go back. For instance, the example that I gave here, for instance, just this polynomial times the Gaussian, it doesn't have any double roots later because it's not optimal. If it was optimal, it would have several double roots after the last sign change. Okay, so let me talk about the connection with sphere packing. Okay, so so basically the sphere packing problem is you have a bunch of spheres that you want to place in Euclidean space in such a way that they are similar spheres, equal radii, and they can't overlap. And you want to arrange them in a way that you have the largest possible density. And okay, so basically the way of measuring density, you just measure the density in a big cube, and then you send that to the big cube to infinity, and you take the limit sup of those densities. That's how you define the density of a packing, for instance. And so what we know about this problem is, okay, so I define here delta D to be the sphere packing density of RD, meaning the largest density among all possible sphere packings of RD. So in 1910, we found out that the honeycomb was already conjecture, has the largest density for R2. And then if you just make a laminate packing, basically put a honeycomb on top of another honeycomb and so on, and make this way you produce the cannonball packing, and which is the best one in R3, about 70%. And in 2016, Marina Wiazowska proved that the E8 lattice, if you consider the E8 lattice as the positions for the center of your packing, and then you put balls according with the the smallest distance between 2 points in the packing, divide that smallest distance by 2, that will be the radii of your packing. So you place the balls with these centers, and this produces the best sphere packing in dimension 8. And the leech lattice, the same thing in dimension 24. So I guess Marina proved that in 2016, like showed the proof in a conference, and like 1 week later, the people in the conference came up together, figured out how to do it in dimension 24, and then they put the paper on arXiv like 7 days later. And the proofs are almost identical, like just with a little trick that was required in dimension 24. Okay, so that's so how Marina did this. Basically, it's what's the connection here. So for that, I have to explain this linear programming bounds for sphere packing. So how can we prove that a packing is optimal in some dimension? And that's what Kohn and Elkis did in their paper in 2016, 2003. So basically, you have this class of auxiliary functions, which I'm calling ALP of D. Again, they are even real valued. In their case, they already asked for to be radial. They don't bother to do the further reduction to radial. So you have radial functions in RD, and then you ask that both F and F hat to have mass 1. Oh, by the way, I didn't mention what the normalization of F hat I'm using. It's the one with the 2 pi I, of course. So that's the class, and then F has to be positive definite, meaning F hat has to be greater or equal than 0. And then F has to be eventually negative, so meaning minus F has to be eventually non-negative. So the picture here in your mind should be, you have a function that starts at 0, and then it does something, and it starts at 0 being 1, sorry, and it does something, and then it becomes less or equal than 0 outside the ball, and then it stays less or equal than 0. While its Fourier transform is 1 at the origin, and it's just positive, okay, everywhere. That's the picture here. And then what you do, in a similar way, you try to minimize the last sign change of R of F, so the infimum of R of F among functions in here. And so what they show that is if you take the density of this, the packing density of RD, which are defined as delta D here, which is greater than the density of any packing, because this is defined as to be the supremum among all densities of all packings, sphere packings. So that thing is less or equal than something, which is just the volume of a ball radius a half, times this quantity ALP to the power D. So that means that you have an upper bound for packings in RD. No packing of balls in RD can be larger than this quantity on the right, okay? So since the left-hand side is a supremum and the right-hand side is an infimum, basically it means that if you find a packing and if you find a function such that you have equality here, meaning that the density of the packing you produce here equals this volume times R of F to the D, it means that you not only found the best packing, but also the best function in this class here, okay? So this is like a groundbreaking paper that produced several other ones, and so people refer to this paper a lot in this area. So what Marina did, and so what she did was, well, she went ahead, computed the density of the E8 lattice and the delete lattice in dimension 24, and figured out what the number here had to be. Okay, the number here in ALP had to be square root of 2 in dimension 8. It had to be square root of 4 in dimension 24. Okay. So then she had the idea, well, let's build a function that has this bound. So let's build a function in this class such that R of f equals square root of 2. If I do that, then I solve the problem. And it's likewise this for dimension 24. And she ended up doing that by this very magical construction using modular form. So basically the functions that she was considering was a Laplace transform of a certain modular form, if you want a bit more details. And it turns out that in there, that's why I write it in this way, the roots of the function that attains the bound in dimension 8 was square root of even integers. And the first root was square root of 2. So the first time change was square root of 2, solving the problem, but the later roots, which I claim that there must be infinitely many double roots after the first sign change, which was root 2 here, which in the other problem, not in this one. And it turns out that it was always touching a square root of even integers after this point. And in dimension 24, the same, is just that it started as square root of 4 and the other roots were square root of 6, 8, and 10 and so on. Okay. Any questions here?
Yes, Felipe, who was touching function or Fourier transform?
Both.
Ah,
Yeah.
Okay. And one more question. Are there other dimensions where people believe that this Kohn-Yolkis approach will be optimal also? This is one approach, right? It just happens that
Yes.
in dimension 8 and 24, there exists function which does equality here, but are there other dimensions where people also believe that?
The answer is yes and no. Yes, there is one more that people believe, which is dimension 2. But dimension 2, the problem, the packing problem is already solved. But people still want to find the function.
Ah, they don't know function, okay.
Yeah, they don't know the function. Packing is solved in dimension 2, but everybody wants to know the function. The problem there in dimension 2 is that the roots are as there is a problem of the density. The roots are have to be the square root of not all integers, but only certain integers that are representable by a certain quadratic form. And there is a problem there. If you're interested about, there is, so the reason is that I'm saying this because they can't apply the same techniques as in dimension 8 and 24 to dimension 2, because there is this intrinsic problem with the localization of the roots.
And what about other dimensions?
In other dimensions, it's conjecture that it doesn't yield any equality here. Yeah.
Okay, thank you.
But I'm going to show a table in a moment. We'll explain everything. Okay, so it's the link between the sign uncertainty and the LP bounds. So first of all, if you take a function f in this LP class, okay, and you write this other function, which is f hat minus f, that would belong to the A minus class, okay? And the last sign change of this function, f hat minus f, will be less or equal than the last sign change of f, meaning that this guy here is the lower bound for the ALP, okay? Furthermore, if you do numerically, they're exactly the same. So you can run numerics for that because it's not a coincidence. Well, you're writing is the LP problem, which means that you can just run the linear programs in the computer to test this. So basically what you do is you want to find functions to test if this is true. So you just consider a polynomial with a huge degree times a Gaussian and try to optimize in there. And if you do that for this class, for the LP class, and if you do that for the minus uncertainty principle, they match exactly, okay? Which I mean exactly, I mean, if you do 100 digits precision, it will match with 100 digits. That's how exactly I mean. And if you do 200, it will match with 200 digits and so on. And people have no clue why this should be true. So somehow you should be able to invert this thing from a function here in this class A minus, you should be able to write it as f hat minus f somehow. And that's not clear how one should do that. And so what Marina said, if we go in Marina's proof, so as I mentioned before, Marina showed that ALP equals √2 in 8 and 24 dimensions equals √4. But actually, if you go in her proof, she actually creates first a function in A minus and then fixes it to make a function in ALP. So if you go there and just pick the A minus functions, you will see that and use them, you then can prove that the -1 uncertainty principle is actually equal to √2 in dimension 8 and equals to √4 in dimension 24. And then in 2018, we realized that, well, since I'm kind of explaining it backwards, okay? It was not how this topic was conceived, but to realize that we could use Marina's technique to the +1 uncertainty instead of the -1, since they are cousin problems. And then we managed to show that in dimension 12, you still have √2 as the answer. And then we also presented some numerical evidence that all these quantities here should behave as the same coefficient times √d. They're very close quantities. For instance, between the plus and the minus, you can already guess that in dimension 8, the answer was √2, in dimension 12 was √2, and there is a 4-dimensional gap here per se between the minus and the plus, heuristically speaking. And then for that reason, if you just run the numerics and then you see that they are very close and they all should behave like a constant times √d. And there is some recent numerical evidence in connection with modular bootstraps for conformal field theories, which is a topic in physics which I know nothing about, but it's like it's a fancy to say. There is some numerical evidence there because there are some parts of physics that there is this connection with sphere packing. And then you can relate these two things with this linear programming bounds that I was talking about. And if you go through the paper, you will see that the conjecture that the C here should be 1/pi, which if it's true, should be awesome, because pi will show up somewhere. It's always nice when pi shows up. Okay, so this is the table to comprising everything we know. Sorry, how much time do I have more? 5 minutes, how much?
We have about 20 minutes or so.
20 minutes, great. So maybe I could even explain more things. Okay, great. So let me go through this table from bottom up. Okay, so in 24 dimensions, we know that the best packing is the Leach. That matches exactly with the ALP problem by this linear programming bound, which the answer is √4. And the -1 uncertainty principle is also solved. That answer is √4. Have no idea what the +1 should be. In dimension 12, we don't know the best packing. We don't know this linear programming bounds and -1 function, but we do know the +1 uncertainty principle, and it should be √2. So this kind of the +1 problem should be connected with some geometrical problem. We don't know yet what that should be. So the -1 is connected with packing, maybe +1 is connected with some other problem. We don't know. That's like an active part of my research, for instance, try to find a problem for that, a geometrical problem. So in dimension 8, we do know that E8 is the best packing. It matches with the bound, with the LP bounds, which are √2. The -1 is also solved. Again, to solve the ALP, you really should solve the A- first and then fix it to make a function in ALP. So the answer is also the same. In dimension 2, we do know that the honeycomb is the best packing, but we can't find the function that attains it so far. And the answer should be this strange number here for square root, the 4th root of 4/3. And we don't know how to solve the plus as well. In dimension 1, the things are kind of obvious for packing. Obviously, it should be the integers, the centers of the intervals you should choose. And for that, the ALP should be 1 and the minus should be 1. The functions are very simple to construct here. For instance, for the ALP problem, the solution is just the hat function, from -1 to 1, and the height is 1 as well. That will solve the ALP, giving you 1. So if you just do the Fourier transform of the hat function minus itself, minus the function, then you get the solution for the ALP, which is 1 as well. But in dimension 1, we can't solve the plus. And that's really annoying because it should be easy. Like the cousin problem is very easy, and it should be easy for the plus, and we have no idea. And that's what the big surprise will come from. So, and then I want to explain try to explain a little bit what's going on in dimension 1. It should be the easiest problem. It's weird that we can only solve in dimension 12. More or less know the reasons, right, from the packing side, but in dimension 1 should be easy, but we don't know so far. Okay, any questions so far in this table here? Great. So, so in March this year, right in the beginning of this crazy ride that we are together, we put a paper in our arXiv where we extended these uncertainty principles to other things. So in the end, what we realized was that the Fourier transform is not the central object here. Basically, to prove these uncertainty principles, you only need the Hausdorff-Young bounds for the Fourier transform. And if you have that, then you can have an uncertainty principle. So anything that sort of has a Hausdorff-Young inequality associated, you can show an uncertainty principle associated. So in some sense, this explains, it gives more weight to the idea that this is a real uncertainty principle. So for instance, now you, instead of just having a function in its transform, you could just have a function and then an expansion in some orthogonal basis. And you just ask for the coefficients of that orthogonal basis to be eventually non-negative. That will work as well. So for instance, we can prove an uncertainty principle for spherical harmonics. So you can put something in a sphere, which is always nice. And then with radial reduction, you can do some something for the Gegenbauer polynomials, and then later you can extend for Jacobi polynomials. And that's connected with spherical designs in quadratures. So we also put an application for Fourier series and Bessel-Dini series, discrete and Fourier and Hankel transforms. We also have an uncertainty principle in the Hamming cube, and this is connected with we have an application for complexity measures for Boolean functions. And we also have an uncertainty principle for the Hankel and Hilbert transform and other smooth convolution kernels. So it's really a very general kind of idea, and we have a bunch of applications there. But what I don't want to state the main result in the paper. You can just go ahead and read. It's a bit abstract, but if you want, you can just go to the paper, skip the introduction, just read each application separately. It will make perfect sense. Okay. Okay, so what I want to focus now is on the discrete Fourier and discrete Hankel transforms. Because in a way, if you want to understand the continuous case, the continuous uncertainty principles for the Fourier transform, the ones I just explained, you could just try to mimic them in the discrete setting and then see, and well, we always think of the discrete approximating the continuous and see what happens when the discrete start to approximate the continuous. Maybe you can extract some information about the optimal functions by solving the discrete case for a very large residue class. So that's what we're going to do now. So let me just define the discrete Fourier transform. I have to use odd Q here for the residue class, just because I want to say f hat at 0 or f at 0. And for that, it's always nice to have an odd residue class. So that's just the standard unitary discrete Fourier transform. So this defines a unitary operator between functions from Z mod Q to C. And then what we showed was the following: you can define the same classes, do the same things in a very analogous way. So f and f hat, both even and real valued functions. We don't have to ask them to be L1 anymore, they are just vectors. Both with mass. So you have to choose a sign. You have to choose if you're doing the plus or minus one sign uncertainty. So once you choose a sign, you fix a sign here. So these linear conditions, and then as in the same way, you just try to minimize the square root of k of f times k of f hat. So k of f would be just the analogous of the r of f in the continuous case. So just a minimum of the k such that fn is greater or equal than 0 if n is greater or equal than k. Well, this should be, oh, this thing is wrong. It should be q minus 1 over 2 right here, of course. So what we show that, and the theorem is in this inequality here. What we show is that once you define this minimum, then this minimum is greater or equal than a constant, an implicit constant, times square root of q. So that's our result right here. Okay. So basically this mimics the continuous case. It's just that now we have this extra thing here, the square root of q. So basically this is saying that you can't make f and f hat greater or equal than 0. Let's say you take the +1 uncertainty principle. So you can't make f and f hat greater or equal than 0. It's outside a neighborhood of the origin that's very small compared with a square root of q, for instance. That's what it's saying. So usually what we expect, or what we wish, is that the discrete converges to the continuous when q goes to infinity. That's the heuristic here. So really what you have to do is to normalize this quantity. So you divide by square root of q. So once you normalize, then the multiplying constant should converge to the plus or minus 1 uncertainty principles. Okay. So these on the right side, the plus or minus 1 that I just defined earlier in dimension 1. So the minus 1 was 1, the answer here, and the plus 1, we had no clue. Okay, so I want to give some clue what's the plus 1 is. So if you do the minus 1 case first, the discrete case, and you take a q, very large q. Oh, sorry, this q here, this in this graph, this little q. So capital Q is twice little q plus 1. Okay, sorry about that. I should fix this. So if you so capital Q here for this graph here, it's something about 10,000. So if you take capital Q something about 10,000, you try to find the best optimal, let's say, vector there for the discrete case. And then what you do is you can then plot this vector. So you have a bunch of delta functions, let's say. You can plot that by just doing a spline on these functions, or maybe just computing its Fourier transform, replacing the discrete variable by a continuous one, and plotting that. If you do that, you will get a bunch of Gibbs phenomena, which is terrible. Then you make it smooth with your favorite kernel, the Dirichlet kernel. We use the Jackson kernel because it was the best thing. But anyway, you can just plot the result of the discrete case, and you get this function here in solid. And then if the problem, so first you get a sign change which looks like it's pretty much close to 1. So it indeed is looking that it's converging back to the continuous one. So thumbs up, great. Looks like that discrete is approximated continuous. However, in the -1 case, in dimension 1, we don't have a single extremizer. We have infinitely many. We actually have a manifold of infinite dimension of extremizers. So you can't expect what this function is converging to. It's converging to one extremizer, but which one? And we chose the one which produced the best fit, which is this one here in dashed, okay? But anyway, it looks like that the discrete is converging to the continuous. So we can ask, what about the +1? What's the function we get? And this is the plot. So when you do for the discrete one, it looks like that is the sign change, the answer is converging to 1 divided by twice, root of twice the golden ratio, okay? Furthermore, it looks like that the function is this horrendous monster. It looks like that it's vanishing in intervals. So maybe that's why it's so hard to solve the +1 in dimension 1, because the optima looks like it's vanishing in the interval. And so the size of these parts here compared to the size of these bumps here is very small. So that's what we did, and we got this monster here. And we did that with the discrete Fourier transform. There are other ways of doing that directly from the continuous, and if you do it right, we had to use some hierarchy of linear programming, which is called semi-definite programming, and you got also a similar picture. So we actually have now 2 approaches. This discrete one that I'm talking about, and some other one that produce more or less the same picture. So we're really confident that the function that this thing is converging to really vanishes in intervals, which is completely crazy how to think of producing a function like this. I have no idea how to produce a function that vanishes at intervals, even more to be self-dual. This thing is self-dual. So the Fourier transform equals itself very closely. And it's crazy. So that was the big mystery, and this is the big mystery and surprise at the same time. So I could write this number here on the right by other ways. I could factor this, but I want to write it this way because this comes from another thing, okay? So what you can do is, so you have the discrete, for each Q, you have an answer for the optimal discrete uncertainty principle. Let's call it K. And if you plot this function, you will see that it's like a staircase. So when you go from Q1 to Q2, this thing doesn't increase and suddenly increase by 1. And then you go from Q2 to Q3, but nothing changes and suddenly jumps by 1, okay? So you can kind of invert this function as it jumps, okay? So now we define the jump function, which will be the inverse of this function here. And if you try to compute this limit here, which what we were doing before, then it would be equal to this other one if the jumps were more or less compared. So if the K+1 jump was more or less the same thing as the K jump, okay? So if you do that, it turns out that numerically the -1 jump exactly matches this function here for every single K. So you go numerically, compute what the K should be, and it turns out that it matches this from K up to 100, for instance, which would mean that the vector is of size like 50,000. It matches this precisely. And if you do for the plus uncertainty principle, so Q is always odd, so we subtract 1 and divide by 2. And this is approximately K-1 squared times the golden ratio, you take the 4 function. So it's pretty close. It matches exactly with the first 5 terms, and then it's just off by 1 from some time, and then just off by 2. So it looks like it's very close. And the way we figured out that is that we computed this function on the left, went to the online encyclopedia of integer sequences, put the sequence there, found that it was exactly that, and then was like another big surprise and mystery why this thing is going on. Anyway, so this was another, let's say, evidence that our conjecture is now true, which is that this thing is converging to this. So now we think that this number here is the answer of the +1 uncertainty principle, continuous one in dimension 1, and the function should look like this guy here. Okay, so almost done. So what you can do just to make sure you're doing the right things. So let's define this UK to be this function is VK, this guy, and this guy is computed numerically, okay? So what you can do is you want UK divided by VK to converge to 1, because they should be very close to get to the same thing. So for instance, you can, so the yellow guy here, you can just take VK divided by UK, subtract 1, they should be converging to 1, take the absolute value, multiply by K, and that's the function you get. You could divide it by just an offset by 1, so you could divide by UK plus 1 instead, and also multiply by K, and then you get the function in red. And you can even be crazy and take an off by 2, and just again do the same thing. And you see these 3 guys like yellow, red, and green, and they look like the yellow doesn't want to go over 1, red wants to go to 1, and green starts increasing but then starts decreasing. So this just shows that these 3 guys want to be bounded, for instance. Bounded would be enough. It looks like, even not so precise, but it looks like that eventually they will converge to 1, but we don't care. As long as they're bounded, it means that VK divided by UK converges to 1, because I'm multiplying by K anyway. So if that thing is bounded, so VK divided by UK is converted to 1. And the magenta picture here is just testing if the jump function is comparable with, so consecutive jumps are comparable. So if you take VK and divide it by VK minus 1, so these are testing if 2 jumps are comparable. So this has to converge to 1. So then you multiply by K and it looks like it's decreasing to 2. So it looks like, yes, the jump function is really comparable. So consecutive jumps are really comparable in the sense that we're testing if this thing is true. So it looks like it's true by the graphs. So therefore, this limit should be really this limit here, if this limit exists, if any of the 2 exist. So these are just numerical tests. So it looks like we are in the right direction. And also, if you take the VK function, so it should go quadratically, and you can make an easy test to see what's the leading coefficient of the quadratic expression. So what you do, you just take VK, subtract VK minus 1, divide by 2, divide by K. So that should be the leading coefficient if VK is a quadratic function. So then that should be the golden ratio because it should be comparable to UK. So you subtract the golden ratio and multiply this whole thing by K to 1.5. And you get this function here, and this line here is around 7, more or less. So it looks like that this function here wants to be bounded and oscillate around 7, which would imply that really the leading coefficient of VK is indeed converging to the golden ratio. And the rate of convergence is something like 1 divided by K to 1.5. It's converging even like nicely. And so this just piles more and more evidence that we should really have this thing going on here. And So I think I'll finish here. Thank you.
Okay, thank you very much, Felipe. Please, are there any questions?
Yeah, I will ask one question. So this graph has spikes. Is it because of numerical computation, or is it because the actual graph will have these little spikes? It doesn't look very smooth.
Yes, you're right. So this graph here had spikes as well. And as I said, we had to smooth it out by multiplying by a Jackson kernel. The same way here, if you don't multiply by a Jackson kernel, this will oscillate like crazy. And that's what usually happens when you approximate a function by Fourier series. It's just that this function, the oscillations in this graph were much worse than the oscillations in this one. It looks like that this function is not so smooth. But in any case, there is also a problem, which is the numerics for this problem here, converging much slower than the numerics for the minus. And there is no explanation so far for that. And we don't know why there are even some methods that work very well for the minus, which I'm not going to explain, but doesn't work at all for the plus. And there is some weird reason behind which we don't know. So yes, there are spikes here. Presumably, if you go to very large Qs here, then you have like a ceiling and a floor function and something oscillating in the middle, and these should, in the limit, converge together. But you should get a bunch of oscillations, which are very hard to remove in general. You can see if you do splines and you can kind of smooth out things in there. If you do by Fourier series, also you have to multiply by a kernel, but you can't remove all the oscillation. You remove in the first part, and you see the first part is very nice here up to this point, and then it starts to get, so presumably if you go to very large Q, then the first, like from 1 to 10, you get something very smooth and then something very oscillating later.
Okay, may I ask one more question? So you have this discrete problem, and then you have this continuous problem, and there is this limit. What makes you think that discrete problem should be easier to solve than continuous one?
So in principle, there is no reason. It turns out that numerically, the discrete is behaving much better than the continuous. As long as Q is small. When Q gets large, it's approximating the continuous. So, but at least we can, so I feel like, at least, so this is part of a series of applications in our paper. And in this part, I feel like experimental physicist trying to get the first picture of a black hole. If you look online, the picture of the black hole, you would expect something like in a movie, but it's just like a blur with some black thing in the middle. You know, that's the black hole, but at least it's something. They can get something qualitative about it. So the same way here, at least they can see that it looks like it's vanishing at intervals, and that's already nice. That gives me a direction. But other than this, I can't trust very much this graph, let's say, beyond 5 or 6.
Okay, do we have any other questions? Okay, all right. Well, thank you so much again to the speaker again, and thank you all for coming, and I hope to see you all again next week.